An important technical property of the systematic part is that the model needs to be identifiable. The linear model is not identifiable if some predictor is a linear function of the other predictors. Let us take an example. Assume that we have 4 observations and the model matrix is as shown here. So we have the model includes intercept because we have this column of ones, and then we have 2 predictors x1 and x2 here. Oh, sorry, define so that the first column is x1, vector x1, the second column is x2, and the third column is x3. So they are all vectors of length 4. But now we have that this vector x3 can be computed using vectors x1 and x2 using this formula. So twice x1 plus twice x2 is equal to x3. For example, 2 times 1 plus 2 times 1 gives 4, 2 times 1 plus 2 times 2 gives 6, and so on. So we need that this formula here is true. And also the following 2 formulas hold naturally. So we see that x1 can be written also as a linear function of x3 and x2, and x2 can be written as a linear function of x3 and x1. And naturally, in some cases, we also can have cases where not all other predictors are needed to find a linear formula for x2, which means that actually some of the weights can be zeros, like in this case the weights are half, 1 per 2 and minus 1, and then naturally they can be 0 as well. Let us take another example of the non-identifiable model. So let us consider a case where the predictors of the model can get only values 1 or 0. These are commonly needed whenever we are using dummy variables as a predictors, for example, in analysis of variance and related models. In this case, we have, so again, the x1 can be written using x2 and x3, and also it means that also x2 and x3 can be written using the other 2 predictors. Okay, why is this linear relationship of predictors then a problem in the linear model? The problem is that if we have an unidentifiable model, the parameters of the model are not used. And this means that many values of beta can lead to the same value of xb. Again, let us take an example, following the example 2 above. So we rewrite matrix X here, and if the regression coefficients get value 1, 2, and 3, then our xb becomes, so it becomes, when we compute it, we get vector that is 3, 3, 4, 4. But however, some other selection of beta could also, or will also lead to the same value of xb. For example, let vector beta 2 include 0, 3, and 4. Now x beta 2 is also the same as before. And in the linear modeling, our aim is to estimate the values of beta. But now if we have an unidentifiable model, we can have several solutions that give equally or equal value for the systematic part, and therefore such a model, the beta parameters cannot be estimated for a model that is not identifiable. These 2 values of beta are not the only ones that give x beta is equal to 3, 3, 4, 4, but actually there are infinitely many possible values of beta that give this kind of solution. And this is because our X matrix has columns that are linearly dependent. And in matrix terms, we say that model matrix X needs to have full column rank in an identifiable linear model. There is one important consequence from this definition or from this requirement, namely the number of predictors in a linear model can never be higher than the number of observations in the data. That is, n needs to be higher than p in the model, where n is the number of observations and p is the number of predictors, including the intercept. And in the case where the number of predictors is equal to the number of observations and the model is identifiable, that means that the none of the columns is a linear function of the others, then xb is equal to y, x beta is equal to y, so this means that the residual errors are 0 for all observations. So it means that the model fits perfectly to the data, the systematic part gives exactly the values we have in the data, or the values of y.